Question 5. Given f of x equals log a x, where a is greater than 0, such that s with x coordinate 1/3 and y coordinate -1 is a point on the graph of f, prove that a equals 1. Alright, so first we must have a look at our graph and look at what function they've given us. Now it's important that you're able to recognize a log function. And a great way to do that is to always bring it back to an exponential function, because a log is basically the inverse of an exponential function. So what I mean by that is if we have y equal to ax, x is in the exponent now. So for any a with a changing variable x in the exponent, what would a graph like this look like? And that will always look like this. Like so. And you might have heard of the expression increasing exponentially. That's exactly where this comes from. Exponential graphs increase astronomically quickly. It's incredibly difficult to comprehend. But if we had, for example, and now this is how it comes back to the log graph. If we had, for example, 4 equal to 2 to the x. Now this is also an exponential graph, but we, for example, know what the y value is equal to. Now this is very easy to solve. We can already see that 2 to the power of 2 would equal 4, but let's say it was very difficult to see that. We could use logs on our calculator to find that value of x, which would make this expression equal to 4. And how we would do that is, we'd say, all right, log, and it's always base first. That's why it's always log base, and then the next variable. So log base, and what's our base in this example? It's 2, so we'd say log 2. And our answer, and you always then go to the answer. So it's always log base answer. So log base 2, and our answer here, for example, is 4. So then we'd write 4 on our calculator, and this will pump out 2. So with this little bit of theory, we can now solve this problem. So we need to prove that a equals 3. And in this example, a is the base of log. But you may be wondering now, okay, but wait, we don't know y, we don't know x. How can we solve a? Well, let's just work the exact same way we did here, but just a tad differently. So we have log. We want our base, and x is here, and this is all equal to y. So now we have a look. What other information did they give us though? Oh, wait. S is a point on our log graph. All right. And just quickly to mention this, when you take your exponential function and you turn it into a log function like this, your exponential graph flips in this manner, like so. So it always runs like this. So it will always go, here's the exponential, and the log of that exponential will always look like this. So the asymptote is here for the exponential, and the asymptote is here for the log. So this would be, for example, log the base and x, and this would, for example, be a with our exponential x. Okay, but with that little bit of information, let's continue to solve this. Now, a lot of you might know what the answer is already, but I'm just trying to give all the necessary theory and background, because logs are very important. You need to know how to work with them. So if we have now the point S, we can actually solve what a can be. All we need to do is work around that. So at this point S, and if this is our function for this pink graph, let's plug in, just like we would do with a linear function, straight line or quadratic, exact same manner. So be minus 1 equal to log a is the value we're trying to find, which is the base, and x in this case is a third. All right, now you might be thinking, in equations, usually you do the reciprocal to the one side to get rid of like a third. You times it by a third, and then it will be 3 on the other side. That's how you would simplify. But now what on earth do you do with a log? Well, it's the exact same premise. We are doing the reciprocal of log, and that would be a exponential graph. So how can we turn this log graph into its exponential version? How can we turn this log graph into its exponential counterpart? Well, remember, we always deal with a base and an answer. So the base here in this case for its exponential graph would be a, its answer would be a third, and the value we're trying to find would be the value that the a would be to the exponential of would be minus 1, because usually what we're doing is we've got a to an x equal to y, and we know a, that like I did the example prior, we know a is 2, we don't know x, and we know that y is 4, and then we would use log the base, the answer, and that will pop out 2. But now we're working backwards, and we're finding instead the base we want, because we have the x and y values for the log graph. So now we have 8 to the negative 1 equals a third. So that's the same as saying a over 1 over a equal to a third. And now it's just simple algebra. We're solving for a, so let's bring this on the top here. We can do 3 here, a here, and we've solved it. I didn't realize. We wanted to prove that a equals 3, and we've exactly done that. So just to reiterate, we were given a log function, and we used our knowledge of how exponential graphs relate to log functions and how they look. So we know how they look. And we plugged in an x and a y value for our log graph, and all we did is solve for a. And that is the problem solved.